Okay, I'm going to get started. Wanted to start with just a very quick summary of the last couple of classes. So over last Tuesday's class and last Thursday's class, we talked about rigid bodies and in particular, rigid body equilibrium and rigid body motion. And to understand and explore rigid body equilibrium, rigid body motion, we had to introduce torques and understand the concept of torques. Torques create rotational motion like forces create translational motion. And we had to understand some properties of rigid bodies. We had to understand the center of mass. That was one property that we talked about. And we had to understand moment of inertia. That was the second property that we talked about. That's in addition to the most basic property of mass or inertia of a body, for example, a rigid body. Okay, today's class, I want to concentrate on some examples and illustrations of rigid body equilibrium and rigid body motion. Actually, what we're going to do is really work through some famous examples or classic examples of rigid body equilibrium and rigid body motion. One is it's a famous problem in physics, right? Everybody in physics knows this problem. It's the painter on the ladder. And another famous classic problem in physics is the bucket on the pulley. And we'll look at those two problems and we'll look at a couple of other problems as well. Okay, so this slide and the next slide is just a quick reminder of the equilibrium and non-equilibrium of rigid bodies. So just as a reminder, if a rigid body is in equilibrium, that means that the net force, the total force, and the net torque, total torque on the rigid body add up to zero. And if that's the case, then the body won't accelerate and it won't have angular acceleration. And if it's at rest, it will stay at rest. So that's rigid body equilibrium. This kind of Zen meditation collection of rocks is in equilibrium. Those rocks are experiencing forces and torques, but the sum of the forces and torques on those rocks is zero, and they are in equilibrium. They're at rest, they're staying at rest. Rigid body non-equilibrium. That's when the sum of the forces on a rigid body or the sum of the torques on a rigid body or both, they are not zero. In that case, there's a change in the rotational or the translational or both motion of the rigid body, and the rate of change of the translational or rotational motion of the rigid body is in proportion to the net force and net torque that's acting on the rigid body. And that's described by Newton's second law of translational motion. That's the upper equation in this slide, this little guy here. And the rotation is described by this second equation. That's Newton's law of rotational motion on this slide. In these equations, so you see the net force that's acting on the body on the left, you see the net torque that's acting on the body on the right, you see the resulting linear acceleration, angular acceleration on the right-hand side here, and you see a couple of important quantities. They're the mass or inertia of the rigid body, that's the m. They're the moment of inertia of the rigid body, that's the I. And the m and the I play the role of being kind of the numbers or the values or the quantities that reflect the body's resistance or reluctance to having its translational rotational motion changed. So those are what we call inertias. The inertias against having your translational motion change, or the inertias against having your rotational motion changed. Okay, so let's get on with some example problems. And in this little problem, you can see a picture of when I was younger, I was painting houses. And we're painting this house here, and I'm standing on this ladder. And this is a famous physics problem of the painter and the ladder. And the physics problem part of this problem of the painter and the ladder is how high up the ladder can the painter safely climb without the ladder falling or sliding down. And so we're going to explore this, and we'll discover it depends on ultimately the friction of the ladder with the ground. And we're going to relate the friction of the ladder with the ground to the safety of the painter on the ladder. Let me just walk through some of the physics ingredients of this problem. So here's the first point I want to make, that the painter on the ladder, the painter is exerting a clockwise torque on the ladder. So the painter standing on the ladder, he will tend to try and rotate the ladder clockwise towards the ground, about the base of the ladder. On the other hand, the wall's force on the ladder, that tends to try and rotate the ladder counterclockwise, away from the ground. And part of the equilibrium that's happening when the painter stands on the ladder and the wall is pushing on the ladder is that the torques that are created by the painter on the ladder and the wall on the ladder are in opposite directions. They're in equal sizes. And so the net torque from those two torques of the ladder and the wall cancel out. Okay, second point I want to make about a couple of forces that are acting on the ladder. So there's actually a force from the wall on the ladder that's pushing the ladder. If you look in this picture, it's pushing the ladder towards the left. There's another force that's acting on the ladder. There's the frictional force with the ground, and that's pushing the ladder to the right. And those two forces, the wall's force on the ladder to the left, the frictional forces force on the ladder to the right, those two forces are also in opposite directions and equal magnitude. So those two forces also add up to zero net force. And again, that's the translational equilibrium of the ladder. So this balance of the two torques from the painter and the wall gives rotational equilibrium. This balance of two forces from the frictional force of the ground and the normal force from the ladder, that gives translational equilibrium. And that's the equilibrium that's going on when the painter stands on the ladder. So it's quite an interesting situation. It's quite a complicated, subtle situation. Now, here's the most interesting point. So as the painter climbs the ladder, these torques due to the wall and the painter, they actually grow. They increase. The forces exerted by the wall and the frictional force with the ground, they also increase. So you can't see it when you climb a ladder, but you might want to remember it when you climb a ladder. As you climb a ladder, there's increasing torques that are trying to turn you and the ladder clockwise and counterclockwise. There's increasing forces that are trying to push you and the ladder to the left and to the right. And those are growing as you climb up the ladder. The maximum safe height that you can climb up the ladder. So that's the height before the ladder will slide away from you and fall down. That maximum safe height is the moment, the instant that the frictional force from the ground reaches the maximum frictional force. So that's the safe height that the painter can climb the ladder. And ultimately, we're going to find that maximum safe height in terms of that frictional force and the coefficient of friction. So that's our plan. Okay, to have a quantitative problem with some numbers, I've thought of this particular situation. We've got a 784 Newton painter weight, climbs a ladder of weight 295 Newtons. That has a length of 4 meters, and it's leaning against the wall at an angle of 53 degrees above the horizontal. And using that information and the coefficient of friction between the ladder and the ground, that is the reason that there is a frictional force between the ladder and the ground, and the reason that the ladder just won't slide. We're going to calculate the maximum safe height, the maximum safe distance the painter can climb up the ladder. So that's going to be our problem. So, of course, what did I do next? I drew a diagram of forces that are acting on the ladder. And so that's what I've done on this diagram. So let me just walk you through this diagram a little bit, because it's quite a complicated diagram. Over here on the right, you see the wall. Over here at the bottom, you see the floor, or the ground. In blue, you see the ladder. And the ladder here is at 53 degrees to the horizontal. And the ladder is 4 meters long. So it's exactly the conditions of this problem. Okay, we knew a couple of other things. We knew the weight of the ladder, that was 294 newtons, and I pictured that as acting at the center of mass. And we know that there's a painter on the ladder, and I pictured it as a spherical painter. And we know the weight of the painter is 784 newtons. So the force of the painter on the ladder, standing on the ladder, I've indicated that. The force of gravity on the ladder, I've indicated that. And I've called them WP and for the weight of the painter and WL for the weight of the ladder. Okay, so those are two obvious forces that we were told actually, but there's other forces that we need to add to this picture, and they're the forces due to the wall and due to the floor. So let's walk through those. Upstairs here, we said the wall was smooth, which means that there's no friction. There'll just be a normal force. And so I drew that normal force, called it N subscript W for the normal force of the wall. Downstairs here, the ladder's on the ground and there is friction, there must be friction. So I drew both the normal force of the floor, called it N subscript F, the normal force of the floor, and the frictional force of the floor, called it F subscript F, the frictional force of the floor. And so those are the two forces that are two distinct forces from the floor. Now, all those three forces from the wall and the floor, NW and F, FF, we don't know them right now. We don't know what they are. And to solve the problem of how high the painter can safely climb the ladder, we're going to have to figure out these three forces. And so that's going to be an important part of our problem solving. I make some remarks over here on the left-hand side. So this situation is equilibrium. You know, the painter's standing on the ladder and the painter are at rest. So the sum of the forces and the sum of the torques must add up to 0 in this situation. It's rigid body equilibrium. Is the rigid body equilibrium of the ladder. And as I say, the moment the ladder would fall, or the moment the ladder that will slip, is when the normal force exerted by the wall, which is pushing towards the left on the ladder, exceeds the maximum value of the frictional force from the ground, which is pushing towards the right on the ladder. So when this guy exceeds this guy, that's when the ladder will fall. So that's what we got to figure out. And actually what we're going to do is focus on that moment when they're exactly equal to solve this problem, when the frictional force and the normal force of the wall are the same. Okay, so that's a good picture of the forces. Let's go on. Okay, the next 3 slides, I'm just going to calculate 3 numbers. And I'm going to go through these next 3 slides pretty quickly. I've reproduced the picture of the ladder and the wall and the floor on all of these 3 slides. Nothing is going to change about the picture of the wall, the floor, and the ladder and the forces. All I'm going to do is work through calculating lever arms. You might remember, didn't mean to do that. You might remember that you could write the torque exerted by a force in terms of a lever arm, a distance we call d. And the way you calculate lever arm is think about the axis of rotation that you're worried about. So I'm going to think about the axis of rotation as where the ladder meets the ground. Think about the force and where it's acting. Let's think about the wall's force upstairs here. And draw a straight line from the force along the line at which the force acts. And then the shortest distance between that line along which the force acts and your axis of rotation, that's the lever arm. So this guy here is the wall's lever arm. And if you look, the wall's lever arm, the ladder, and that line along the force, they make up a right-angled triangle. Since you know the length of the ladder, you know the angle of the ladder with respect to the horizontal, you can figure out the lever arm, which is the opposite side of this triangle. It's the length of the ladder times sine of 53 degrees, and here it is. So that's a useful, we're going to use this wall's lever arm when we calculate the torque that is exerted by the wall. And so it's a useful way, a handy way of calculating the torques using the lever arm. There's 2 other lever arms that I want to calculate. So the second one that I want to calculate is what we call the ladder's lever arm. So the weight of the ladder also will create a torque. In this case, we're worried about or thinking about the torque about the axis of rotation of the ladder downstairs here on the floor. And so again, we can calculate the weight of the ladder's torque about that point, that axis of rotation, by again drawing a line along the action of the force. Here it is. That line together with the ladder make up a right-angled triangle. Here it is. And since we know the angle in the right-angled triangle downstairs is 53 degrees, we can create the, we can calculate the lever arm, here it is, for the force of gravity on the ladder It's the length of this line here. This time, notice it's adjacent to the angle of 53 degrees rather than opposite the angle of 53 degrees. Also, notice this time that the hypotenuse of the triangle is not the entire length of the ladder, but half the length of the ladder. But anyway, if you take this right angle triangle, you can calculate the lever arm for the ladder. And that came out to be 1.2 meters. So that was the second lever arm that I've calculated. There's one more. Let's do that quickly. And that's the lever arm of the painter, the weight of the painter. So that's another force that's acting on the ladder. And so I'm calculating that lever arm on this slide here. So here's the painter on the ladder, some distance or height up the ladder. I called it h. And that's going to create a torque. The painter's weight on the ladder is going to create a torque. So again, if we want the lever arm associated with that torque, think about the force, think about the line along which the force acts. That's this vertical line here. And the lever arm will be the closest distance that line gets to the axis of rotation. So it's this distance here. And we can find this distance, again, by a right angle triangle. This distance is going to be, this is adjacent to the angle of 53 degrees. It's going to be the height of the painter up the ladder times cosine of 53 degrees. So this time, it's not a number. I'm not calculating a number for the lever arm of the painter, but I am calculating an expression for the lever arm in terms of the painter's height up the ladder. And so that's the third lever arm that I need. So just to summarize that, those last three slides, let me just go back. I calculated the lever arm of the wall's force on the ladder. It was 3.19 meters. I calculated the lever arm of the ladder's force on the ladder. It was 1.2 meters. And I wrote down an expression for the painter's lever arm on the ladder in terms of his height up the ladder, the thing that we want to find. Okay, so now with those three lever arms, I'm going to solve the forces, the various forces that are acting on the ladder from the wall, from the floor. And in that way, we're going to figure out the maximum height the painter can climb the ladder. That'll be the very last thing we do. I'm going to calculate this force first. That's what I was trying to remember. That is the normal force of the floor. And I'm going to calculate that force by applying equilibrium of forces, specifically the equilibrium of the vertical forces. So let's look at the diagram and take a look at what forces act vertically. There's actually only three forces acting vertically. There's the weight of the ladder that's acting downwards over here on the right. There's the weight of the painter that's acting downwards in the center here. And then there's the normal force of the floor that's acting upwards. So those are the three forces that are acting vertically. And because the ladder's in equilibrium, those forces must add up to zero. And with that idea, that concept, we're going to find the size of this normal force. And so here's where I do that. I wrote the sum of the three vertical forces. There's the normal force, NF, from the floor. There's the painter's weight. There's the ladder's weight. And those must add up to zero. The directions, well, the normal force was up. I was going to call that the positive direction. The painter's weight is down. I'm calling that the negative direction. The ladder's weight is down. I'm calling that the negative direction. And so this is equilibrium in the vertical direction for the forces. Now, I know the two weights. The only thing I don't know is the normal force. And so I can rearrange this equation for the normal force. And the normal force must simply be the sum of the two weights. The weight of the planer is 784 newtons. The weight of the ladder, 294 newtons. So the normal force must be 1,708 newtons to balance those two weights. And so we've solved for one of the forces on this slide. Okay, next slide. Next slide, I'm going to apply equilibrium in the horizontal direction. And actually, with this slide, I can figure out the two remaining unknown forces, which are the wall's normal force and the frictional force from the floor. So I'm going to do that. So this slide, I'm going to solve for the frictional force of the floor, the normal force of the wall, by the equilibrium of the forces in the horizontal direction. So let's see how this must work. What are the forces that act horizontally? Well, upstairs here, it's the normal force of the wall that's acting towards the left, and downstairs here, that's the normal force of the ground on the ladder that's acting towards the right. They're the only forces acting horizontally. All the others are acting vertically. Well, I can write down the equilibrium condition for those two forces, that the frictional force towards the right, I call that the positive direction, must be balanced by the normal force of the wall towards the left. I call that the negative direction. Those two must add up to 0. That means, look, here is what it means. It means that the normal force of the wall must equal in size the frictional force of the floor. And we know that the frictional force of the floor is nothing other than the coefficient of friction times the normal force on the floor, and we know that normal force. So this will allow us to solve for both the normal force of the wall and the frictional force of the floor. So let's do that. I plug in the coefficient of friction, I plug in the normal force of the floor from the last slide, and I figure out the normal force that's exerted from the wall and the frictional force that's exerted from the floor. They're both 485 newtons. Look, at this point, I've solved for all the forces from the planer, the ladder, the wall, and the floor in this problem. And now we can figure out the maximum height that the planer can climb to. So that's the final step. Let me go to the next slide. So on this slide, I want to calculate the planer's height up the ladder. That is the maximum safe height, the highest he can climb before the ladder will tip. And when the ladder tips, there's no longer zero torque on the ladder. There's a non-zero torque on the ladder. So it's just at that moment before that happens. So I'm going to figure out the painter's maximum height. I'm going to figure it out by now thinking not about the equilibrium of the forces, but thinking of the equilibrium of the torques. And so that's what I'm going to do on this slide. I'm going to think about the equilibrium of the torques about the base of the ladder. That's downstairs here. Now, as you know, if I'm going to think about the equilibrium of the torques on the ladder, if I think about it about this point, I don't have to worry about the forces that act at that point. So there's the frictional force, and then there's normal force of the floor at that point, but they can't create torques about that point. The only forces I have to worry about are the weight of the planer, the weight of the ladder, and the normal force of the wall. Those are the only forces I need to worry about at this point in terms of the torque that's going to be exerted on the ladder about the base of the ladder. Okay, so let me write down the sum of the torques on the ladder. There's the torque that's exerted by the wall. So that force was NW, and its lever arm is DW. There's the force that's exerted by the ladder's weight. That's W subscript L, and its lever arm was DL. And then there's the force exerted by the painter. That's the weight of the painter. And that force was WP, the weight of the painter, times the painter's lever arm, which was D subscript P. Now, if you look at that equation, the really magic thing about that equation is, well, look, at this point, we know all the forces. We know NW, WL, and WP. So we know all the forces. We know the lever arm of the ladder. We know the lever arm of the wall. The only thing we don't know is the lever arm of the painter. And so I can rearrange this to calculate, in terms of all the other quantities, the lever arm of the painter. And so we can solve for the maximum lever arm of the painter before the ladder will fall. And so I rearranged the equation. I took the term with the painter in from the left to the right-hand side. I divided through by the weight of the painter. So you can see I get the weight of the painter in the denominator here. And over here is the lever arm of the painter. And every number, the three forces on the right-hand side, I know them all. The two lever arms on the right-hand side, I know those two. I can plug them all in, and I get the lever arm of the painter. It's 1.53 meters. And so that's the lever arm of the painter. It's actually interesting that I didn't really draw things quite right. And I didn't know this at the time, right? The painter lever arm is actually larger than the ladder's lever arm, i.e. that the painter is higher up the ladder than the center of mass of the ladder. So I drew the painter as below, he's safe there. He's below the center of mass of the ladder, but he actually can climb up higher than the center of the mass of the ladder. So maybe he's up here somewhere. Okay. So now we got the painter's lever arm, but remember, the painter's lever arm is related to this distance, this height, h, of the painter up the ladder. I can rearrange that equation for the lever arm. I can rearrange it for the height of the painter up the ladder. And if I do that, it comes out to be 2.54 meters. And so that is the minimum height of the painter up the ladder. And this is a classic example of rigid body equilibrium involving rotational dynamics, rotational equilibrium, and translational equilibrium dynamics. It's a classic example of calculating torques and calculating forces. It's really a problem that wraps up so many of the different things we've talked about this semester. Okay, it's also a long problem, right? I don't want to hide the fact that it's not an easy problem that we just solved. It's a tough problem that we just solved, but we've answered an important question for the painter. We've answered the important question of how high could that painter climb? And we did it by understanding all the things that are going on with that ladder, all the forces and torques that are exerting on that ladder. Okay. I'm going to show you a quiz. I'll give you a quiz, but first I'm actually going to show you a little video of the painter climbing the ladder and when the ladder will fall. And then we're going to do the quiz. So I'm going to share a different screen here. Okay, so here I am in the large lecture room. I've almost forgotten where it is, but I did find it. And I'm going to show you this demonstration with the painter climbing the ladder. And so here's the ladder. I'm showing you here that it is a real ladder that somebody could try and climb. and I put the ladder against the wall. And look, now we know so much about this situation. There's the weight of the ladder being pulled down towards the center of the earth. There's a force from the floor on the ladder that's both a normal force and a friction force. And then there's, for this smooth wall, there's a normal force from the wall on the ladder. So all those forces are there. Now I've got to get a painter. Okay, so here comes the painter, and the painter is going to start climbing the ladder. And so here's the painter beginning to climb the ladder. And of course, the painter now adds a force to the ladder, adds torques to the ladder. That means that the normal forces of the wall and the frictional normal forces of the floor on the ladder are actually changing when the painter starts to climb. They're growing when the painter starts to climb. But still, despite the additional torques and forces of the painter, the ladder is in equilibrium, staying in equilibrium. It's at rest, staying at rest. Okay, so we're going to ask our painter to climb a little higher up the ladder. I'm starting to get nervous. And he's climbed now halfway up the ladder, roughly. And at that point, again, the painter's forces, torques on the ladder have increased. The forces of the wall and the forces of the floor and the torques that are created by the forces from the wall and the floor, they're also increasing. But the ladder was still in equilibrium. It was at rest and staying at rest. So we'll have the painter climb some more. Finally, we found, experimentally, the maximum height that the painter could climb to. At that point, we exceeded the maximum frictional force from the floor. And because we exceeded the maximum frictional force that was needed, the ladder slid. Okay, so now I want to give you a quiz. The quiz asks whether the maximum safe height that you can climb up the ladder depends on the angle of the ladder, and does that height increase with increasing angle, or does it decrease with an increasing angle? I mean, you could solve this from the equations that we calculated for the ladder and the height on the ladder, but also you could think, and so we could do that, and I could go back to the equation, but let me just do it from a more practical, common sense point of view. Suppose that angle was really tiny. Supposing the ladder was almost horizontal. You step on the ladder, that ladder is just going to slide to the ground. If you make that ladder nearly vertical, that ladder is very stable. So in the case where the ladder is nearly horizontal, it's going to need a huge frictional force to just stop it sliding to the ground. In the case where the ladder is almost vertical, it barely needs any frictional force to hold it stable. So you might notice when you see painters painting that they look like they're putting the ladder very steep against the wall. I might be tempted to put it less steep. It seems less dangerous, but actually they're doing the right thing when they put the ladder very steep against the wall. When you put the ladder very steep against the wall, you need less frictional force between the ladder and the ground to keep the ladder stable. And so it is the safe thing to do to put the ladder as vertical as you can manage, because the less vertical, the smaller the angle with respect to the ground, the more unstable the ladder and the painter will be. Okay, so let me move on to a second example now. The last example was one of rigid body equilibrium. This is one of rigid body non-equilibrium. So we're going to talk about this. So in this problem, let me get the pen going. In this problem, we got a bucket that's going to get lowered down a well. And so the arrangement involves this pulley up on the right here, and this bucket down on the bottom left here. And the bucket and the pulley are attached by a rope. And for concreteness, we're told the mass of the pulley, we're told the radius of the pulley. The pulley's a cylinder, and we're told the mass of the bucket. And we're going to release the bucket, and we're going to try and answer from our understanding of rigid body dynamics, rigid body motion. We're going to try and understand the acceleration of the bucket as it falls down the well, and the tension in the rope as the bucket falls down the well. So that's going to be our goals. And so this is, again, a very famous problem in physics involving rotational dynamics and translational dynamics of rigid bodies. And so that's the reason we're working through this problem. That's the reason for this problem. Okay, so I want to say a few words about what's then going on in this problem. And then we'll go on and solve the problem. So this problem, in the last problem, we just focused on the ladder and the forces and the torques on the ladder. But in this problem, we really have to focus on these two distinct rigid bodies, the bucket and the pulley, or the bucket and the cylinder. So when the bucket falls down the well on the end of the rope that's attached to the pulley is going to undergo rotational motion. And actually the pulley just undergoes pure rotational motion, just rotates about its center, rotates about its axis. On the other hand, the bucket, when it's falling down the well, it's just undergoing translational motion. Undergoing pure translational motion. There's no rotation of the bucket. And so this problem involves translation of one object, the bucket, and rotation of another object, the pulley. Now, the key thing is that the bucket and the pulley are tied together by the rope. So the rotational motion of the pulley and the translational motion of the bucket, they are related to one another. They're joined to one another. And we can solve the acceleration of the bucket, the angular acceleration of the pulley, the tension in the rope. We can solve all those things by joining together the description of the motion of the rotational motion of the pulley and the translational motion of the bucket. Join together the Newton's second laws that describe the rotational motion of the pulley and translational motion of the bucket. And that's what we're going to do. Supposing the rope was not there. Well, you release the bucket, it just falls towards the bottom of the well with the acceleration of gravity, 9.8 meters per second squared. And the pulley doesn't move at all. Now, when you have the rope there, what happens is that the falling of the bucket towards the bottom of the well is actually braked, slowed by the tension in the rope. And so we'll discover that the bucket accelerates towards the bottom of the well when it's attached to the rope with a smaller acceleration than the acceleration of gravity. And the other thing that happens, of course, is that the pulley starts rotating as the bucket starts falling. Okay, so here's a key point. Without this key point, you can't solve this problem of the bucket and the pulley. The key point is that the rotating motion of the pulley, rotational motion of the pulley here, and the falling motion of the bucket, they are related motions because the bucket and the pulley are attached by this rope here. Now, here's the specific relationship. Over here on the left-hand side, these would be the coordinates describing the motion of the bucket. So its position, vertical position, its velocity, its vertical velocity, its acceleration in the vertical direction. These are all the all the parameters, quantities that describe the translational motion of the bucket. Over here on the right-hand side, these are the quantities that describe the rotational motion of the pulley. So the angle of the pulley, the angular velocity of the pulley, the angular acceleration of the pulley. They describe the pulley's motion. And those two things are related by these equations here, because the pulley is attached to the bucket, or the bucket's attached to the pulley by this rope. And in particular, they're related in this way if the rope doesn't slip or slide on the pulley. And they're related through the radius of the pulley. So this R is the radius of the pulley, and that determines the relationship between the linear coordinates describing the translational motion of the bucket and the rotational coordinates describing the rotational motion of the pulley. So that's really important, and we need this. This is super important. We need this to solve this problem because it connects for us the rotational and translational motion. Let me go on to the next slide. Okay, so my first step in solving this problem is I'm going to think about the bucket, its translational motion, and I'm going to apply Newton's laws of motion to that bucket. And then I'm going to separately think about the pulley, its rotational motion, and I'm going to apply Newton's laws of rotation to the pulley. So let's do that. Applying Newton's laws of motion. This slide is all simply applying Newton's laws of motion. I started over here on the left-hand side by making a sketch of the problem. Of course, I would always, like the ladder, I sketched the ladder and drew the forces on the ladder. Here I'm going to sketch the pulley in the bucket and sketch the forces that are acting on the pulley in the bucket. So that's what I'm doing. Let me start with the bucket. Here it is in magenta. And I know the mass of the bucket, so I indicated that. And then I know that there's two forces acting on the bucket. We've met this sort of problem before. There's the weight of the bucket acting downwards. There's the pull of gravity. There's the tension in the rope that's acting upwards. And so I call that weight W. I call that tension T, as we normally do. So that's the bucket force diagram. And then I've also got the pulley. So up here is the pulley in green. The pulley is rotating clockwise as the bucket falls and the rope extends outwards. And I know a bunch of things about the pulley. I know the radius of the pulley. I know the mass of the pulley. And we were told that the pulley was a cylinder, so that we know the moment of inertia of the pulley in terms of the mass and the radius of the pulley. I looked this formula up. This is the moment of inertia, rotational inertia of a pulley. Okay, so we know all that about the pulley. And we also know there's actually a couple of forces acting on the pulley. One would be the force of gravity that acts at the center of mass. But I didn't draw that because it doesn't create a torque, because it acts at the center, geometrical center of the pulley. I did draw the tension force from the rope that's acting on the pulley. That doesn't act at the center of the pulley, that acts on the circumference of the pulley, and that does create a torque. So that's why I drew this guy here. So this diagram that I constructed, well, it has all the information we're told on it, which was important to collect together. So we have a summary of that. It also shows the forces that are acting on the bucket and the torques that are acting on the pulley, which are critical to writing down the equations that describe the translational rotational motion of the bucket and the pulley. Okay, so let's start with where we're going to start. Translational motion of the bucket. Let's apply Newton's second law of motion, F equals ma, to the bucket. Well, there are two forces that are acting. There's the weight of the bucket, that's mg. There's the tension that's of the rope that's acting on the bucket, that's the T. The weight is downwards, so I indicated that as the positive direction. The tension is upwards, so that must be the negative direction. Those are the two forces that act. They add together through Newton's second law to determine the acceleration of the bucket. They add together to be equal to ma, mass times acceleration. And so this equation here, I labeled it number one, is important. It's the one describing the translational motion of the bucket. I did the same thing for the rotation of the pulley and Newton's laws of rotational motion. So Newton's laws of rotational motion say that if you sum the torques acting on a rigid body, that equals the moment of inertia of the rigid body times the angular acceleration of the rigid body. It's the rotational analog or mirror or twin of this translational law of translational motion, F equals ma. Well, then I went on and filled in what are the torques that are acting on the pulley. As I said, there is in principle, there's one force, the weight, that acts on the pulley, but it acts at the center, and so the weight creates no torque. So I could have written a 0 here. But then there's the tension in the rope that does create a torque because it's exerted at the circumference of the pulley, a distance r from the axis of rotation. And so that tension force T creates a torque that's the size of the force T times the distance of the force from the axis of rotation times the the sine of the angle between this displacement vector and this force vector. That's 90 degrees, so that would just be 1. So that's the sole torque that's acting on the pulley, and that determines the angular acceleration of the pulley through Newton's second law of rotation, this little guy here. And again, the left-hand sides are analogous in this law. They're either sum of forces or sum of torques. The right-hand sides are analogous in these laws. They're either containing the accelerations or angular accelerations and the inertias or rotational inertias. It's worth standing back from these two equations we just generated and thinking about what we know in them, what we don't know in them. So we know the parameters of the pulley and the bucket. So we know, for example, the mass of the bucket, the mass of the pulley, the radius of the pulley. So we know those things, but we actually don't know yet the acceleration of the bucket, acceleration of the pulley, angular acceleration of the pulley, or the tension in the rope, those things. So how are we going to solve that? I mean, it's nice, right? It's nice that I've written down the laws that describe the translational rotational motion, but how am I going to solve those laws for the quantities that we want? So let's see how we can do that. I'm going to put the chat back up because I forgot to do that. Okay. Let me go on to the next slide. On the next slide, most of it I just stole from the previous slide. You'll recognize it. Here's the diagram. I just reproduced that. Here's the laws of motion, rotational, translational. I just reproduced that. But I added a couple of things. Here they are upstairs. I added this relationship that we discussed between translational and rotational motion, that the linear acceleration of the bucket, A, the angular acceleration of the pulley, alpha, are related to one another through the radius of the pulley. So with that, I'm able to eliminate alpha and replace it by A. The other thing I fed in is that The cylinder, we were told the pulley is a cylinder, it has a moment of inertia 1/2 mr squared. I filled that in too. So both of these equations I plugged in to the equation of rotational motion. An interesting thing happens when you do that. So one thing that happens is that you end up replacing the angular acceleration with the linear acceleration. The A and the alpha were related. The other thing that happens is actually when you plug in the moment of inertia, you find the radius of the pulley cancels out and you're just left with the mass of the pulley. So that's interesting. So now we've got the old version of the translational Newton's laws equation, and we got kind of a new version of the rotational Newton's laws equation, this one here. And if you look now, I'm stepping back, right? I'm rolling backwards because I'm a rolling rigid body. If you step back and look at those two equations, you see that now there are two equations with two unknowns. We don't know t, we don't know a. We can find t and a by mathematically solving the two equations for the two unknowns. We turn this sophisticated physics problem of the bucket falling down the well into a simple mathematical problem of solving two equations for two unknowns. So let's go ahead and do that. Here I'm going to do that. So on this slide, again, I'm partly just, here's the old picture of what's going on, recycling that. And here are the two equations that we had developed from our understanding of translational rotational motion of the bucket and the pulley. We want to solve these two equations that contain two unknowns t and a for the a and for the t. So I spotted, this is how smart I am. Not really. I spotted that there's a minus t and a plus t in equation 1 and equation 2. I spotted that if I add together equations 1 and 2, the t's will cancel out, and I'll be left with an equation. The sum of the two equations just has one equation with one unknown. And so that's what I did. When you add two equations together, it means adding together the two left-hand sides, adding together the two right-hand sides. And so I'm going to go ahead and do that. When I add together the left-hand sides, the minus t and plus t cancel out. I just get mg. When I add together the right-hand sides, I've got a common factor of a, so I pulled that out. And so I've got the mass of the bucket plus half the mass of the pulley times the acceleration of gravity. Sorry, the acceleration of the bucket. Well, look, this single equation with one unknown, I can rearrange it for the acceleration, the quantity I want. The acceleration of the bucket is the acceleration of gravity. That has to be there because it is at least falling under gravity, multiplied by some factor. This is just a number, doesn't have units. It's a number that is sort of comparing the mass of the bucket and the mass of the pulley. And this number, right, has to be smaller than 1, because in the numerator, there's just the bucket's mass. In the denominator, there's the bucket and the pulley's mass. And so it has to shrink, make the acceleration of gravity smaller. Has to make the acceleration of the bucket smaller than the acceleration of gravity. And if you plug in the numbers, you get 5.3 meters per second squared. That's the acceleration of the bucket. And it's almost half the acceleration of gravity. Once you've got the acceleration A, it's easy to go back. You could go back to equation number 1. You could go back to equation number 2. I went back to equation number 2, rearrange it and solve for the tension. And so that's what I did here. The tension, according to equation number 2, is half the mass of the pulley times the acceleration of gravity. That tension comes out to be 13.2 newtons. Let me show you what am I going to show you? I'm going to show you a demonstration of this. I'm going to share a different screen. here we are. And what you're seeing is a pulley. Here's the pulley. And I'm going to attach a bucket to that pulley. And we're going to release the bucket in the pulley, just like in the problem. And we're going to watch the acceleration of the bucket towards the bottom of the well. So here I come. I look like a bit foolish, I would say, but I'm going to drop this bucket down the well. Now the first thing is I'm actually going to just drop the bucket. No, I don't drop the bucket. I never did that. I'm going to just drop the bucket down the well. I'm going to put this on slow motion. I'm going to rewind it a little bit. And I'm going to release that bucket, and it's on half speed here, but because I wanted you to see it as much as possible. But that acceleration is about half the acceleration of the acceleration of gravity. And you notice that as well as the bucket accelerating, the pulley also underwent angular acceleration. So it's a combined motion of the bucket and the pulley. Okay. There's one more problem I'm going to work through in the last 10 minutes, but I think I'm going to show you, it's a related problem, and I'm going to show you the video of that before we solve the problem. And this is also a very famous physics problem, and it's the yo-yo. And it's actually really related to the bucket falling down the well. We're going to see that. I'm going to show you another video now. This one I'm playing the whole thing on half speed, mainly just for effect, but also because I'm going to drop this yo-yo. This green yo-yo, I'm just going to release it, and it falls under gravity towards the ground. So that was the yo-yo falling at 9.8 meters per second squared towards the ground. It was very hard to see it in the movie. Now I'm going to let it fall by holding onto the string. And so let's see if we can see it when it's attached to the string. And it falls way slower when it's attached to the string. This is also a problem involving rotational and translational motion. I'm going to go back to my slides now, if I can. Let's see. Okay, this is also a problem of rotational and translational motion. I'm going to get chat back on as well if I can. Except that in the case of the bucket and the pulley, one object was translating and one object was rotating. In the case of the yo-yo, it's one object that's undergoing both translational motion and rotational motion. But we're going to solve, here's a picture of the pulley in this overhead. So, sorry, picture of the yo-yo in blue in this overhead. On this picture, I've drawn the string that's wrapped around the yo-yo. And we're going to find the downward acceleration of the yo-yo when I'm holding the string or the rope, and we're going to find the tension in the rope. And again, so that we can be a bit quantitative, in this problem, I'm going to treat the yo-yo as a solid sphere. I've got to get the pen going again here. I'm going to treat the yo-yo as a solid cylinder. Its mass is 15 kilograms. Obviously, the real one wasn't 15 kilograms. I wouldn't be able to pick it up. Its radius is 0.12 meters. Obviously, the real one wasn't 0.12 meters. But these are examples of a mass and a radius of a cylinder that we're going to let fall like a yo-yo. And we're going to, as I say, calculate the acceleration and calculate the tension. Acceleration of the yo-yo and the tension in the string. So let's go ahead and do that. And we can do this problem a bit quicker, which we need to do because it's related to the prior problem. Okay, so first point, as you saw in the movie, right? Without the rope, the yo-yo just undergoes translational motion. With the rope or the string, the yo-yo undergoes both translational and rotational motion. And actually, without the rope, it falls at 9.8 meters per second squared under gravity. With the rope breaks the yo-yo, slows the yo-yo's fall, and that acceleration is less than 9.8 meters per second squared. And it was quite a lot less than 9.8 meters per second squared in the video. Again, the rotational motion of the yo-yo and the translational motion of the yo-yo, the falling motion, the rotating motion, they are related to one another. And they're related to one another by this set of equations that we've met several times now. We met them in the last class, we're meeting them in this class. They correspond to when the rope or the string does not slip or slide on the yo-yo. In that case, the downwards translational motion of the yo-yo, that's over here on the left, is related to the rotational motion of the yo-yo about the center of mass through these equations. So for example, the acceleration downwards of the yo-yo is related to the angular acceleration, rotational acceleration of the yo-yo through the radius of the yo-yo. And so are the velocities, so are the angles and positions. So that's an important part of this problem. We can then write down, next step, it's kind of like the last problem. I can write down Newton's laws. I can apply Newton's laws to the motion of the yo-yo. And this time we got a yo-yo that's undergoing both translational motion and rotational motion. So upstairs here is my analysis of the translational motion of the yo-yo. Downstairs is my analysis of the rotational motion of the yo-yo. And I'm consulting this picture that I constructed. Here's the yo-yo in light blue. I know its mass, I know its radius, I know its moment of inertia in terms of the mass and the radius. Here's the rope in black that's wrapped around the yo-yo. There's a force of gravity in magenta that's pulling the yo-yo downwards. And because I know its mass, I know its weight is 147 newtons. There's a force of tension due to the rope that's acting upwards on the yo-yo, but I don't know its size. The weight does not create a torque on the yo-yo because it's acting at its center of mass. The tension does create a torque on the yo-yo because it's acting at its radius arm. And so this picture encapsulates the forces and the torques that are creating the translational rotational motion on the yo-yo. Okay. So let's write down Newton's second law for the translational motion. Here it is. There's the weight downwards, mg. There's the tension upwards. I'm using plus and minus signs for the directions of up and down. Those are the two forces that act on the yo-yo. They add together to make the acceleration, to determine the acceleration of the yo-yo according to Newton's second law of translational motion. Similar thing for the rotational motion. Let's apply Newton's law of rotational motion to the yo-yo. There's two forces that are acting on the yo-yo. There's the weight, but it acts at the center, so it creates no torque. There's the rope's force. It acts at the radius of the yo-yo, so it does create a torque. And that torque is T, the tension force, times R, the distance from the axis of rotation. Actually, I used little r in this equation here, so it's this little r here. Just a point here that might have got confusing because I've seen it in the chat. I've been using in these problems a T and a tau. So a T is the tension force. The uppercase T is the tension force. If you see a tau, this should be a tau here, that's the torque. That's the torque that's acting. Okay, so these are the two equations that we built that describe the translational motion would determine the acceleration, describe the rotational motion that determines the angular acceleration. If you look at those equations, again, the accelerations are unknown. The tension is unknown. We want to solve those two variables. Okay, so at that stage, I just copied the last slide and added a couple of things. And I did this on the previous problem with the pulley and the bucket and the well. I added in there's no slip condition. That relates acceleration and angular acceleration. I added in the fact that my rotating object is a cylinder with a moment of inertia determined by its mass and its radius. I added that in. When you do that, you get a modified second equation describing the rotational motion that can go with the original first equation describing the translational motion. It's these two equations, upstairs here and downstairs here, that we're now going to solve, because those are two equations containing two unknowns. They contain the unknown acceleration of the downwards acceleration of the, I've forgotten what it's called, yo-yo, and they contain the unknown tension in the string that's attached to the yo-yo. So now I can just do the math of solving this problem of two equations and two unknowns. Here it is. On this slide, the upper equation is the one describing, whoops. Here it is. Upper equation is the one describing the translational motion. Lower equation describing the rotational motion. I notice again, I've got a plus and a minus t in these equations on the left-hand side. It means I can add together the two equations to cancel out the t's, get this equation here that relates the unknown acceleration of the yo-yo downwards to the acceleration of gravity. And if I rearrange it, I get this little equation here. Acceleration of the yo-yo is 2/3 the acceleration of gravity. And then I could go back to either the first equation or the second equation, rearrange those for the tension in terms of the now known acceleration, and I get that acceleration, that tension. Okay. Well, today's class, we've worked through three examples involving rigid body motion, one involving equilibrium, two involving rotational motion, and they are actually classic examples, famous examples of rigid body motion. In the next class, we're going to turn to another topic, rigid bodies and their motion. We're going to turn to the topics of rotational energy and angular momentum. They're parallels of kinetic energy and linear momentum, or momentum in translational motion. So we're going to explore those in the next class.